how much his passion is for lung mechanics and ventilation. And I'm sure this topic is going to really excite you also. Over to Dr. Farhan.
Thank you so much for the kind introduction. Good morning, everybody. My topic is monitoring of stress and strain without using esophageal pressure monitoring. And let us see whether it is possible. So I'm going to briefly review the basics of respiratory physiology, and then we'll go to the concepts of stress and strain. And then we will discuss the PEEP-step method for assessing the stress and strain. So we all see these numbers on the screen of the ventilator, the peak inspiratory pressure, the mean airway pressure, and the positive end expiratory pressure. This is called as airway pressure. And this is the pressure which is used to open the lungs as well as elevate the chest wall. While the transpulmonary pressure is the pressure which is used to only expand the alveoli and the lungs, not the chest wall. And it is measured as a difference between airway pressure and the pleural pressure. Airway pressure, as we saw already, it is displayed on the screen of the ventilator, while the pleural pressure is measured indirectly from measuring the esophageal pressure most commonly. And the transpulmonary peak inspiratory pressure is the difference between the plateau pressure, which is displayed on the screen of the ventilator, and the pleural pressure at the peak inspiration. Transpulmonary pressure at expiration is the difference between positive end expiratory pressure and the pressure measured by the esophageal pressure monitoring during expiration. And just like driving pressure, which is difference between the plateau pressure and PEEP, the transpulmonary driving pressure is the transpulmonary pressure at inspiration minus transpulmonary pressure during expiration. This was a landmark study by Chumulo et al. On 80 patients with ARDS, and he demonstrated that these numbers which are displayed on the screen of the ventilator are poor surrogates of actual transpulmonary pressure. That means if you have a normal chest wall elastance and you have a displayed positive end pre-plateau pressure of 30 centimeters of water, then 25 centimeters will be spent in expanding the lungs, and only 5 centimeters will be used to open the chest wall, elevate the chest wall. While if you have a problem of poor chest wall elastance like obesity, ascites, or chest wall edema, and in that case, you have a plateau pressure which is displayed on the ventilator screen as 30, only 15 will be used in opening the lungs and 15 will be wasted in taking care of the poor chest wall elastance. So what Chumulo et al. Showed was the plateau pressure which is displayed on the surface, on the screen of the ventilator, can be equal to transpulmonary pressure of only 10, or it can be 28. So there can be so much variation. So this brings us to the concept of stress and strain. So stress is basically the transpulmonary pressure, as we saw, the difference between airway pressure and the pleural pressure, while strain is the ratio of the volume which we achieve to the original volume which it was. So usually it is the change in volume to the original volume. At 0 PEEP, when we measure the end expiratory lung volume by various techniques like helium dilution or nitrogen multiple wash-in, wash-out technique, that is the FRC. And then there is a tidal volume on the top of FRC, and when they take the ratio of tidal volume to FRC, that is strain. When we introduce a PEEP in the system, we are basically introducing a certain PEEP volume. And then this is end expiratory lung volume, which is a combination of both PEEP volume and FRC. So delta EELV will be EELV minus FRC, that is PEEP volume. And when you want to measure the strain here, this will be tidal volume plus PEEP volume divided by FRC, that will be the global strain. The relationship between stress and strain, as we all know, is K multiplied by strain. And K is lung-specific elastance. Strain, as we saw already, VT divided by FRC. Lung-specific elastance is the pressure required to double the size of the baby lung. But esophageal monitoring has a lot of technical limitations, even in developed countries. It relies on the correct balloon positioning, gravitational forces. It is not validated in prone positioning. It also depends upon the elastic recoil of the balloon, the esophageal peristalsis, etc., etc. There are a lot of technical issues with esophageal pressure monitoring. And that is why it underscores that we need some alternative tools to measure stress and strain which does not use esophageal pressure monitoring. And that brings us to this question, can we do that? And the answer will depend upon two conditions. First is, you should have an ability to measure FRC. And once you have FRC with you, then you can take ratio of VT divided by FRC and calculate strain, simple. And FRC can be measured by various methods like electrical impedance tomography. It can be measured by nitrogen multiple breath wash-in wash-out technique in GE ventilators, or it can be measured by helium dilution technique. And then second condition is you should be able to separate chest wall elastance and lung elastance and measure lung elastance specifically. Because once you have lung elastance, as we know, the lung has a tendency to collapse in itself because of surfactant and because of elastin fiber, and chest wall has a natural tendency to expand, and that creates a negative intrapleural pressure. So we have a lung compliance PV loop, we have a chest wall elastance PV loop, and we have airway pressure, which we see on the screen of the ventilator, which is the average of lung elastance and chest wall elastance. And the sweet spot where both equilibrate with each other is nothing but FRC. And we need to separate this chest wall elastance and lung elastance and measure lung elastance separately. Once we are able to do that, as we can imagine, we can measure lung specific elastance, because lung specific elastance is lung elastance multiplied by FRC, and FRC, as we already saw, we can measure as VT by the nitrogen multiple wash-in wash-out technique. And once you have a lung-specific elastance, we already saw stress is equal to lung-specific elastance multiplied by strain. This was a landmark study which was published in 2012 on 13 pigs, and they demonstrated that when the PEEP changes, the proportion of change in PEEP is equal to the proportion of change in the transpulmonary pressure. A very important study. They measured the airway pressure via the pressures which were displayed on the ventilator screen. Pleural pressures were measured by esophageal pressure monitoring, and end expiratory lung volumes were measured through the electrical impedance tomography. Very important thing was they noticed was when the airway pressure was increasing, the PEEP was increasing, they found that end expiratory lung volume was also increasing on electrical impedance tomography, but there was hardly any change in the pleural pressure. This was a very important finding they found. They found that the change in the end expiratory lung volume obtained by the ratio of change in PEEP to total elastance and change in PEEP to chest wall elastance were not correlating, but the delta ELV, which was measured by spirometry, was correlating very well or predicted very well by this ratio, the delta PEEP to lung elastance. That means delta ELV was equal to the ratio of delta PEEP to lung elastance. And if we change this equation, scramble this equation, we can see that lung elastance is equal to ratio of delta PEEP to delta ELV. This means we can measure lung elastance by changing the PEEP. So they found that if your tidal volume was equal to change in the end expiratory lung volume, then your change in PEEP is equal to change in transpulmonary pressure. This is very important finding. That means, suppose this is a pressure volume loop at a 0 PEEP, and you have a driving pressure of 10 centimeters of water at a 200 ml tidal volume, and you are applying a PEEP step. That means you are applying a PEEP high or higher PEEP, which is 80% of the driving pressure. Here the driving pressure is 10, so 80% of that will be 8. So if you apply a PEEP high of 8, and there is another PV loop with the same tidal volume of 200 ml, then you have a delta PEEP, which is this PEEP high minus the 0 PEEP, and you can measure the FRC at 0, and you can measure the end expiratory lung volume at 8 by various techniques, as I said, by electrical impedance tomography or nitrogen multiple wash-in wash-out technique or helium dilution technique, and then you have an ELV. And now you can measure the delta ELV as this ELV minus this FRC, and now you have a delta PEEP, you have delta ELV, you can take the ratio and calculate lung elastance. Once you have lung elastance, the problem is solved. Lung specific elastance is nothing but lung elastance multiplied by FRC. And the condition, important condition is the change, the PEEP high should be set in such a way that this tidal volume which you are generating is equal to the delta ELV. This is very important, and if that happens, then your transpulmonary driving pressure is equal to delta PEEP. Now the question is, how does this magic work? I have shown all these things, but how does it actually work? How does the change in the volume, the delta ELV, when it is equal to tidal volume, the delta PEEP is equal to transpulmonary pressure? This is because during normal inspiration, as I said, when the air enters into the lung, during inspiration, it opens the lung as well as chest wall. But when we apply a PEEP and keep the PEEP sustained for a long time, then As we can see in this schematic presentation of ARDS patient, this is a PEEP of 0, PEEP of 10. This horizontal line is a watershed between atelectatic and open alveoli. And at this line, the pleural pressure is 0 as measured by the esophageal pressure. As you can see, even after application of PEEP of 10, the esophageal pressure is almost same, 12 and 12 to 12, 14. And there is same pleural pressure, no change. And this is because the chest wall has a tendency to expand outwards. And chest wall does not have any sensors. So it doesn't know that there is a PEEP application in the lungs and there is a pressure change in the lung going on. Mathematically, it can be explained like this. As we saw, stress is equal to K multiplied by strain, and strain is nothing but Vt divided by FRC. And K can be expanded. Lung-specific elastance, as we saw already, is equal to lung elastance multiplied by FRC. So that lung elastance is nothing but delta PEEP divided by delta ELV and FRC. So that means FRC will cancel out. And if you adjust your PEEP high in such a way that your tidal volume is equal to delta ELV, then even they will cancel each other. So now your FRC is also going to cancel each other, and mathematically you will have a transpulmonary pressure which is equal to change in the delta PEEP. This is how you can go for calculation of a stress. So this was an experimental lab study where test lung was kept inside a chamber which was connected to another chamber which was 2/3 filled with water, which was connected to another sac which was filled with water, which was representing abdomen. This part which is not filled with water and this part around the test lung was representing the pleural space. This was connected to a pressure gauge which was changing the pleural pressure into negative and positive. There was a strap attached to the chamber in which this test lung is placed, which can control the chest wall elastance. And then the delta ELV during the PEEP steps of 4, 8 and 12 were determined in this isolated lung, and the transpulmonary pressure was calculated as the airway pressure, which was measured here directly, minus the pleural pressure. The pleural pressure is the pressure in this chamber. And they found that when the airway pressure changes and expiratory lung volume changes, the pleural pressure does not change. The same finding which was found in 2012 study in pigs. This was a study in human beings, in 12 adults at different PEEPs, and they also found similarly that change in airway pressure and change in end expiratory lung volume is not affecting the pleural pressure as long as the change in tidal volume is equal to delta ELV. They found that there was an excellent correlation and agreement of transpulmonary pressure based on lung elastance determined by conventional esophageal pressure monitoring and based upon this equation of delta PEEP divided by delta ELV. And one more study on 24 adult patients, and they also found similar study. So scientific evidence based wise, only 3 published studies are there as of now on human beings and adults, and 1 study on pig I already explained, and 1 lab study. So total 5 publications on this unique method, and there is no pediatric published data. In our hospital, we have performed this study, which has sent for publication. And we can see here 63 children were eligible for the study, and we performed this PEEP-step maneuver. We measured the end expiratory lung volume using nitrogen multiple breathe wash-in wash-out technique at 0 PEEP and at PEEP high. But we can see here, interestingly, that only 33 patients were finally enrolled in the study because there are so many children had to be removed from the study because of various technical reasons. Because it is not easy to perform a nitrogen wash-in wash-out technique and measure an FRC at 0 PEEP and then perform a PEEP-step maneuver. So many things can happen. I can't go into the detail of this study. But what I want to say is still it is in this study needs some technical improvements, this particular technique. So we need technological refinement as well as larger muscle-centric studies in children to validate a PEEP-step technique, but it has a promise. What Ola Stringquist in his research paper, in his review paper commented, which was very interesting, is that when choosing between the conventional esophageal pressure method and this PEEP-step procedure, it seems likely that PEEP-step procedure will result in measurements with higher precision. Because esophageal pressure is very inaccurate and it gives you only regional information, not entire lungs information. And as it is a simple, non-invasive procedure, it would probably be preferable actually in many situations, depending upon as scientific progress happens in next few years and we get more refined tools. Thank you very much.
That's an excellent talk, Dr. Farhan.